Hi guys, here are the notes for horizontally fired objects. These problems are very similar to what we've done already with a little bit of a twist. So for this first question, you have to think back what we did the other day. So the question is, which object will hit the ground first if they're launched at different speeds? And if you remember from the launcher in the back of the room, both the spheres hit at the same time. So even though these spheres are launched at different velocities, they would all hit at the same exact time. Because gravity is what's pulling them down. So in order to solve horizontally fired object problems, there's a couple of hints that we need to use. So the first is we have to separate the horizontal and vertical information. This will make more sense once we do a problem in the next page if you're having trouble with these concepts. So we talked the other day, there's no air resistance, there's no jetpacks on the sphere, so the horizontal velocity is constant, which means the x acceleration is 0. And the y acceleration is still gravity. When something's thrown in the air, gravity is what's acting on it. So the initial y velocity is 0. If you throw it perfectly horizontally, the initial y velocity is 0. And when you're doing these, the link in the problems is the horizontal and vertical times are the same. So the easiest way to start these is just to get right into doing the problems. So we look at the next slide. Imagine Sarah driving a stunt car off a 75-meter cliff with a speed of 15 meters per second. First, we want to sketch her path. So if her car went off the cliff, her car would go in an arc down. It would look like a parabola. So now, like I said in the last slide, what you need to do is separate x and y information. So we need to make two charts. With the last problems, we did this chart. So we have y information. But with these problems, they're going horizontally, so we also have x information. So like I talked about, like I mentioned, the x velocity is constant. So with these first two values, the initial and final velocity are the same. The acceleration is 0, so we could simplify the chart in the x direction to v, d, and t. Now we could plug in what we need to. And what I'm going to do is change colors for a second here. So the things you need to know that aren't going to be told to you in the problem are that the initial y velocity is 0. Put a little star next to that. That's what you need to know. And the y acceleration is gravity. Negative 9.81 meters per second squared. So now we look at what we have. We have she is going at 15 meters per second. Her car is going horizontally off the cliff. So put in the 15 meters per second here. And her car falls 75 meters. So that's the vertical displacement. And now since her car goes down 75 meters, we make it negative. So the first question is, how long until she hits the ground? So if you look at the chart, you only have one piece of information in the x direction, so you have to use the y information. And if you have VI, A, D, and you want to find T, we use the formula that we've used a lot. T equals VIT plus 1/2 AT squared. Since I used units in the chart, I don't have to use my units here. So I'm just going to plug in what I have. Sorry about that. And I'll simplify. And if I solve, I get 3.9 seconds. So of the keys in these problems is I'm going to fill this number into the chart. Now I'm going to put it in a different color for you. So we found 3.9 seconds. Now, if we look back to the last slide, the last hint, it says a horizontal and vertical time that's the same. This is the most important part. So if we look, the X and Y time is the same. So this is the most important part in this problem. So if these values are identical. So every time you get for the X is the same time that goes in the Y. So that's really important in solving these. That's how you have to do them. That's the link. So now range. I know in math class, range means Y values, but for us, range means how far it goes in the X direction. So that means horizontal distance. So now if you think back to the only information we have in the X direction, we have V, D, and T. So the basic formula we have from the year with V, D, and T is V equals D over T. So now I'm going to simplify this formula a little bit and just do D equals to VT. Now one hint I forgot to give in the last problem is that when I do these problems, I like to put little subscripts so I know I can keep my information organized. So I want to find X distance, so I'm going to use X velocity. So the X velocity is 15 meters per second. Since I used units up top, I won't use them here. Time the car is in the air is 3.9 seconds. So I just do 15 times 3.9 on my calculator. I get 58.5. That's how far she would go horizontally. So if we could just take a second to go back, I'll put it in a different color. So up here, I should just label them with little y's. Just this helps keep X and Y information separate. So we're almost done with this typical type of problem. So we want to know the vertical velocity on impact, the Y velocity. So the simplest formula we could use is VF equals VI plus AT. We want to find Y information, so I put my little subscripts there. So the initial Y velocity is 0. The gravity is negative 9.81, and it's in the air for 3.9 seconds. So if I use my calculator, I get 38.3. It's negative 38.3 meters per second. It's negative because she's going down. Now the last question ties in to the river problem. So imagine when just as she hits the ground, she has an X velocity. The X velocity is constant, 15 meters per second. She has a Y velocity we just found is negative 38.3, so she's going down at 38.3. So her impact velocity, and if you think back to the river problem, it's the same idea as her resultant. So we find the resultant by doing A squared plus B squared equals C squared. And we just plug in our values. So if we use our calculator, 15 squared is 38.3 squared, and then take the square root, we get 41.1 meter per second. So if we can measure how fast she was actually going, it's that resultant. It's 41.1 meter per second. But in order to solve these problems, we have to break the information up into X and Y. So I hope this helped, and now you can solve the problems on page 1 and 2. Make sure you check the solutions while you're working. I'll see you in class.